I would argue that 3.4, example 4, is probably the most important thing we do in chapter 3. And it's ultimately guiding us to the end result here, which is giving us the ability to solve a cubic equation. Now, in order to get that equation is a little bit tricky in this particular question. It says that Bill has an ice sculpture already, so it's 3 by 4 by 5. That's the volume currently. And he wants to reduce the size of each, the size of each side, there we go, by removing the same amount of ice from the 3 dimensions. Now, what that does mean is that the volume of this block as a function of what he removes, which I'm going to call x, and let's state that. Let's say that x is equal to the amount cut from each side, just so we know exactly what it is. And that allows us to write this volume function. So my new ice sculpture, I guess it's still a cube, is going to be the 3 minus x, because we've taken x off, times 4 minus x, times 5 minus x. Now, it is important that each of those dimensions is a physical quantity. So 3 minus x, 4 minus x, and 5 minus x must all be greater than 0. Now, if we solve those, this tells me that x must be less than 3. Here I get that x must be less than 4. And here I get that x must be less than 5. Now, all of those restrictions need to be satisfied. So the most restrictive restriction becomes what we'll use. And we are going to say that throughout this question, when we solve it, x must be less than 3. And the logic behind that is if you have a 3-foot piece of wood and you cut off 4 feet, how much wood do you have? You can't really have negative wood, so you could only cut off, 2.9999 feet from that chunk, including ice in this case as well. The question then says, so this is the polynomial function to model the volume, but he wants to reduce the volume of the ice to 24, which means that v of x we want to equal 24. So to find out just how much Bill has to cut off each side, we are going to solve when 24 is equal to 3 minus x times 4 minus x times 5 minus x. Oops, messed up my minus sign there. There we go. Looks a little wonky, but that's okay. Now, I think, in the concept of full disclosure, if you were just solving this, if Bill was working this and he had his graphing calculator, he could just graph y1 is 24, y2 is 3 minus x times 4 minus x times 5 minus x, and the intersection that is, less than 3, I should write something else here. We can't add dimensions, so x has to be greater than 0 there as well. Sorry about that. We could use the intersection to solve this. And there's nothing wrong with that, but I want to make sure we know how to do it algebraically as well. So in order to do this algebraically, what I'm going to do is I'm going to expand the right-hand side and then look to get one side equal to 0. So I'm going to say that 24 is equal to, all right, I'm going to do 3 minus x times 4 minus x. That's going to be 12 minus 3x minus 4x plus x squared. And that's multiplied by 5 minus x. So I'm going to say that 24 is equal to 12 minus 7x plus x squared times 5 minus x. So 24 is equal to, so I'll do 12 times 5, that's 60. 12 times negative x is negative 12x. Negative 7x times 5 is negative 35x. Negative 7x times negative x is positive 7x squared. And then x squared times 5 is 5x squared. And x squared times negative x is negative x cubed. Now, to solve this, I'm going to make one side equal 0, collect my like terms. So I will be subtracting 24 from both sides. I get that 0 is equal to, I'm going to put this in descending order of degree. So negative x cubed. Maybe I'll try to write that a little bit more legible. Negative x cubed. So I've dealt with that one. We have 7x squared plus 5x squared. So positive 12x squared. Those two are dealt with. Negative 12x minus 35x is negative 47x. Those two are dealt with. And then 60 minus 24 is positive 40. That's going to be 36. Now, what we need to do is solve the values of x that make that polynomial equal to 0. I don't like it when my highest degree term is negative, so I'm going to multiply it by negative 1. Because one side is equal to 0, that doesn't change that value. Really what I've done is like I've reflected the graph across the x-axis, so any points that were on the x-axis, which are the values of x that make the polynomial 0, haven't changed. And this is definitely just a personal preference. I just really like having my highest degree term as a positive number. All right, from here, we have to basically check and factor this cubic function. So I am going to check the candidates for a, because we want to make sure that p of a is equal to 0. So we know that x minus a is a factor. The candidates for a are the factors of the constant. So if I check 36, I mean negative 36 is okay. I'm going to check either 1 or 36, 2 and 18, 3 and 12, 4 and 9, or 6 and 6. I know I wrote 6 twice there, but you don't really need to. Remember that you are looking at the positive, negative for all those factors. Now, we talked about this in another lesson. You should always check positive 1 first. And hopefully you don't necessarily need a calculator to do so. If I check positive 1 here, I'll write it out. I'm going to look at, so I'll just put maybe P of 1 here. Positive 1 would be 1 cubed minus 12 times 1 squared plus 47 times 1 minus 36. So that's 1 minus 12 plus 47 minus 36. 1 minus 12 is negative 11. Negative 11 plus 46 is 36, and 36 minus 36 is 0. Now that means that x minus 1 is a factor of, and I'll write it out here again, x cubed minus 12x squared plus 47x minus 36. Now I really want to push this concept that lets me know that I could write this as 0 times x minus 1 multiplied by whatever x cubed minus 12x squared plus 47x minus 36 divided by x minus 1 is equal to. And that's a really important consideration, that what I've written in the bracket there, the cubic divided by x minus 1, that's what we would use the long division for. Right? We don't want to leave that as an ugly fraction. Instead, I'm going to do this with synthetic, where I take the coefficients of the cubic, so 1, negative 12, 47, and negative 36. I put the value that makes my divisor 0, positive 1 in the bottom. The first number drags down, then I multiply. I add downwards, so this is going to be negative 11. That means this is negative 11. That means this is 36. This is 36. I'll put those arrows in there, and finally I get 0. Now that's important because it allows me to replace that division statement with 0 is equal to x minus 1 times x squared minus 11x plus 36. And now I look to factor that quadratic. So in order to factor that quadratic, I'm looking for two numbers that multiply to 36 and add to negative 11. Fortunately, I've already written out all the factors, and none of them add to negative 11, which may mean that it's not factorable, or it may mean that we're going to get some, very odd exact values. Really importantly, that this has two solutions. Either x minus 1 is equal to 0, so x could be 1. Now I'm going to put foot behind that. That's a valid answer. If we take 1 foot off each dimension, that's less than 3, bigger than 0, that should work. But we could have another solution, which is when x squared minus 11x plus 36 is equal to 0. The easiest way to check an unfactorable quadratic is to use the quadratic formula. So the values of x that make that 0 are negative 11 plus or minus the square root of negative 11 squared minus 4 times 1 times 36. Ooh, that's a problem. That's going to be a really big number. Divided by 2 times 1. If you have your calculator, and hopefully you do, this is math after all, I'm going to say here that x is equal to 11 plus or minus the square root of, so negative 11 squared is 121 minus 4 times 1 times 36, and we have a bit of a problem because we get the value inside that radical, inside that square root is negative. Now, hopefully you remember what we call that. That's called the discriminant. Because the discriminant is negative, I'm just going to put that x has no solutions. And that's an important thing, that quadratic, is never equal to 0 for any real number. So it means the only possible solution is x is equal to 1 foot. Now, what we are saying here, and I want to summarize, that we are saying that v of x, let's write that first, is equal to 3 minus x times 4 minus x times 5 minus x. But we're also saying that v of 1 is equal to 24. And I think we should check that really quickly. I want to see what v of 1 is. V of 1 is 3 minus 1 times 4 minus 1 times 5 minus 1, which is to say 2 times 3 times 4, which is 24. So Bill, I think that was the name, needs to cut 1 foot off each dimension. All right, bit of a weird question. And again, I want to push the concept that 3.3 allows us to factor and therefore solve a cubic equation, which is what we got in this question. All right, I'm going to put that assignment up. It's got the review page as well. Check Google Classroom because we are modifying these as we go, and keep plugging away at this math because it will work, or you'll understand it a lot better with plenty of practice.